Got an exciting one planned for you today. We're going to look at electric flux, which makes time travel possible, and then move on to Gauss's law, which is related to flux, and it is one of the four fundamental equations of electricity and magnetism, part of what is called Maxwell's equations. Let's get to it. Flux, as defined by our good friend Wikipedia, is a nice simple concept. It is ubiquitous as well, and it describes the flow of a variety of physical properties. In our case, we are interested in the flow of the electric field. If you take this analogy with a river flowing to describe flux, well, you've got the speed of the water, and that can be thought of as the strength of the electric field. But then you also need the size of the river, its width and depth, so we need to multiply the electric field by an area. And this quantity here is going to give us the electric flux. And the symbol for electric flux is a capital Phi. Some people say Phi. And a lot of times we put a subscript E here just to remind ourselves that it is electric flux. Later on we will look at magnetic flux. And so here we go. We just need the electric field times the area. Now we already know a little bit about the electric field. We know that it's proportional to the number of field lines per unit area. So this is field lines. Because we said as field lines are more densely packed, that corresponds to a greater electric field. So if we rearrange this and say that the number of field lines is proportional to the electric field times the area, this thing was equal to our flux. So we can also say, this is kind of a good way of conceptualizing electric flux, it is the number of field lines going through a certain area. So in our picture over here, the flux is the number of field lines going through this surface here, or it's proportional to that anyway. So if you have a larger surface in this constant electric field, you'd have more field lines and you have more flux. Or if you have the same surface but a stronger electric field, then you would also have more field lines through here. So you would have more electric flux. Now it does get a little bit more complicated, because if we imagine having this same rectangle here, a line perpendicular to our electric field, then there's going to be more field lines going through it than if it is at some angle. And if you think about it at some really wide angle here, then you're going to have very few field lines going through it, so that means that there's less flux going through that. So we have to take into account the orientation of the surface and the electric field. So a more robust definition of our electric flux is EA times cosine theta, where we define theta as this angle here, the angle between the electric field and the line perpendicular to the surface. And we can call this a vector dot product. The electric field is a vector quantity, and we can describe the area of our surface as a vector whose magnitude is the area and whose direction is perpendicular to the surface itself. So we can do that. When things are not quite so nice and tidy with constant electric fields and constant angles, then it gets a little more complicated still. So in this case, if you have an electric field that's diverging and therefore it's getting weaker, you're going to have different strengths of electric field. And if you have some odd-shaped surface here, you're going to have different angles for each of these. So you might have guessed it, we have to use our good friend the integral, and we just take the electric field dotted with each little infinitesimal chunk of the area, and then we add all of those up, and we can still get the electric flux that way. Most of the time we're going to have situations that are highly symmetric, and we don't have to worry about doing something like this. So here is our flux equation in all its glory. A lot of times, this is for any surface. We could use this equation here. More commonly, we are going to be interested in the flux through closed surfaces. And so we write our integral with a circle here to tell us that this is over a closed surface. We're doing a surface integral. So the idea is, here I've got a closed surface and I want to know the flux, total flux there, or if I want to know the flux through this surface surrounding a charge here, these are going to be closed surfaces, as opposed to the previous slide where we just had one surface and the flux going through it. When we have a closed surface, we also have to be concerned with the sign of our flux. Field lines flowing into the surface get a negative sign, and field lines flowing out of the surface get a positive sign. If we just have a single surface like this, it doesn't really matter because of what is in and out, so you can just talk about the flux. But when you've got a closed surface, you need to be careful about positive and negative flux. A couple of examples of how flux can be applied. If I have a cube now in a constant electric field, well, the 6 sides, here, 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 I guess that's only 4 sides, and the back that we can't see, there are no field lines piercing those sides, so we know that the flux through those sides is 0. And then we could find the flux through this side and the flux through the other side if we knew the magnitude of the electric field, and then we've got the dimensions here so we could find the area. So we could just do E times A for each side. And because they have equal areas and the electric field is constant, we know that on this side it's going to be negative EA, over here it's going to be positive EA, and the total flux would be 0 for this situation. Here's another example. If we wanted to find the flux through this curved surface here, that might be a little bit tricky because the angle, I don't know why I don't have the electric field coming all the way through, but it should be. Missed my mark there. Anyway, the angle between the electric field and the surface is always changing, so we're going to have to integrate, and it's going to be a bit of a pain. But if we realize that the flux coming out of this surface is exactly equal to the flux going into a surface bounded by that, then we could just find the flux going through that circle, which is going to be a lot easier because the electric field is perpendicular at all points, so we can just do whatever the electric field is times the area of that circle, and that will equal the flux coming out the back. Granted, that would be negative and that would be positive, but we can deal with all of that just fine. Alright, why we care about flux is because flux is integral to Gauss's law, which I already mentioned is one of the 4 fundamental equations in all of electricity and magnetism. So what Gauss's law says is that the electric flux through a closed surface, so we've got our closed integral here, is equal to the enclosed charge, so that's the charge inside of our surface, divided by epsilon naught. Gauss's law is going to be your friend. It makes life a lot easier. Granted, we can only apply it to certain situations with quite a bit of symmetry, but we can choose any surface we want to enclose our charges, and then we can find the electric field due to those. I'll go through a number of examples here, and hopefully you get the hang of it. So if we wanted to confirm the electric field from a point charge, we already know this. It's kq over r squared, or 1 over 4 pi epsilon naught times q over r squared. By the way, if you look at Gauss's law, there is an epsilon naught here, and you can write this in terms of k, so you'd have 4 pi k q enclosed. But we like to have it simpler, which is why a lot of times we use epsilon naught even in Coulomb's law, because Gauss's law is considered more fundamental, and so we like to get the more fundamental equations to be as simple as possible, and there's no real reason for that other than aesthetics. Alright, so we're going to look for this, and if we apply Gauss's law, we can say E dot dA is equal to Q enclosed over epsilon naught. And in this situation, I've just got a charge Q, and I want to know the electric field at any distance from that charge. So I can choose a surface. That's what this green thing is. That's what we call a Gaussian surface. This is the same Gauss, by the way, who gave us Gaussian distributions. Smart guy. Anyway, I can choose some odd-shaped surface and make things very hard on myself, or I can choose a nice spherical surface, in which case the electric field is perpendicular to the surface at all points, and it is also an equal magnitude as long as I'm at an equal radius. So as long as my sphere is centered on that charge, then this becomes really easy. The electric field is constant, so at that location, so I can just have E. Then so I can pull that out, so it's just going to be the integral of dA right? And the integral of dA is just going to give me the surface area of a sphere, which is 4 pi r squared. I can set that equal to the enclosed charge. In this case, I just have a charge q, and then I have my epsilon naught there. I divide this over, and lo and behold, we get 4 pi epsilon naught q over, that's ugly, extend this line out a bit, over r squared, which is exactly what we expected to find, right? Okay, let's look at another, just a conceptual example here. If we want to know the net flux through each of these surfaces, again, just thinking about the field lines helps us out. So this is the case we just did. So the net flux would be Q over epsilon naught. We're not looking for the E field, I guess. So that's our electric flux through A1. Now here, the field lines, every field line that goes in also comes out. And going in is negative and coming out is positive. So the net flux through this guy is 0, which corresponds to what Gauss's law tells us, because it says the flux, electric flux, E dot dA is equal to the enclosed charge over epsilon naught. And since the enclosed charge is 0, then the flux has to be 0. Essentially, if there are no sources or sinks, there's no net flow in or out of the surface. All right, a few more examples. Hang with me. Here we have a charge conducting shell, so you can imagine a hollow metal sphere, and we want to know the electric field inside the shell and outside the shell, and then what if it were solid rather than hollow. So let's start out part A, inside the shell, where r is less than r naught, because r naught is the radius of our shell. Well, we can already see E dot dA is Q enclosed over epsilon naught. There's no charge on the interior. We have a charged shell here, so there's charge residing on the conductor itself. So this is 0, and so the electric field inside, which we already knew because we talked about that with the Faraday cage, the electric field inside is a big whopping 0. If I want to find the electric field outside, where r is greater than r naught, did it backwards up there, sorry. Good thing we have erasers. In that case, E dot dA gives us Q enclosed over epsilon naught. And the electric field is constant at all points if we choose a Gaussian sphere. And it's perpendicular at all points, so this just becomes integral of dA, which is going to give us 4 pi r. The enclosed charge, we're saying the total charge distributed around that is Q over epsilon naught, and this is exactly what we saw for a point charge. So the electric field outside, 1 over 4 pi epsilon naught times Q over r squared. I forgot my squared over there. All right, so it's just like a point charge once you get outside of the sphere. And what if the conductor were a solid sphere? Well, we know that the charge would distribute itself on the outside. So inside, Q enclosed would be 0, and outside Q enclosed would still be Q, so it wouldn't change a thing. No change if it's a solid conducting sphere. All right. Now we're going to look at something a little more complicated. Here we have a solid sphere that is uniformly charged. So the only way this can happen is if it's a non-conducting sphere. You could have like a plastic sphere, and you could get charge evenly distributed throughout, because that charge can't move around if it's a non-conductor. All right, again, we want to find the electric field inside and outside. We'll start with outside this time. Well, we're going to end up with the exact same thing as previously. All of the charge is inside, so E dot dA becomes E times 4 pi r squared. The enclosed charge is the total charge on the sphere, which is Q, so Q over epsilon naught. And you may wonder if Gauss's law ever gives us anything different. It does, fortunately or unfortunately, depending on your perspective. So 4 pi epsilon naught Q over r squared once again. All right, inside it does get a little more complicated. So our good friend Gauss's law, E dot dA equals Q enclosed over epsilon naught. So if I'm at some distance r less than r naught, I'm inside the sphere here, then the entire charge Q is not enclosed. So we have to think about how much charge is enclosed. Well, the total charge is Q, and if we divide that by the total volume, this is going to give us the charge per unit volume. Volume of a sphere is 4/3 pi r cubed. Now we want r naught here because that is the volume of the total sphere. So essentially this is the charge density. And then we multiply that by the volume of the sphere at radius r, which is going to be 4/3 pi r without the naught cubed. This guy should be cubed. Sorry about that. So the 4/3 pi go away, and we get Q times r cubed over r naught cubed. So we still have E is constant at that location, and then dA gives us the area of that sphere, so 4 pi r squared once again, but now we've got a more complicated Q enclosed. So we'll go Q over epsilon naught times r cubed over r naught cubed. R squared cancels out a couple of those. If we solve this guy for E, we get the electric field inside is, let me make sure I get this right, Q over 4 pi epsilon naught. I'm going to throw the r naught cubed on here because that's constant. It's an ugly Q up there. But all of that times r. So there's the electric field inside the sphere. As I just mentioned, those are constant. So if we were graphing the electric field starting at the center of the sphere and moving outward, it would increase linearly, because this is just proportional to r, until you get to an r value of r naught, in which case it becomes an inverse square, and you get it to decay like that, all the way to 0, I guess. Anyway, all right, getting close to done. A couple more examples. They'll go quick. So here I have a line of charge. Now if you remember, finding the E field from a line of charge using the electric field as defined by Coulomb's law and doing that integral was a bit of a pain in the butt. But Gauss's law makes life simple. By symmetry, we know that the electric field is pointing straight outward because any horizontal components will will get canceled out by another point on the line. So that tells us there's no flux going through the ends of our Gaussian surface here. So we can choose a Gaussian surface as a cylinder. Not always, we don't always have to do spheres, because that way it is, again, perpendicular to the electric field at all locations, and the electric field is constant at all locations. So let's jump right in here. We want to find the E field as a function of distance here. So E dot dA equals Q enclosed over epsilon naught. So E is constant, so we just have the integral of dA, which is going to give us the surface area of the cylinder here. And that surface area is 2 pi r, which is the circumference of the circle, times L. And then we can set that in equal to the enclosed charge. Well, the enclosed charge is going to be the charge per unit length, lambda, times the length, L, over epsilon naught. And so these L's go away, and we can go ahead and solve this for E, and we get lambda over 2 pi epsilon naught. So there is our electric field, and it decays as 1 over r. This is the exact same thing that we found by using Coulomb's law with quite a bit more work. Last one, we want to find the electric field from an infinite plane of charge. Remember, this one we also had to do an integral of a bunch of rings. Again, Gauss's law is going to make life easy. E dot dA, Q enclosed over epsilon naught. We can use kind of a pillbox or a hat box shape here that goes through both sides. So the electric field comes straight out, so we don't have to worry about the sides of the curved portions of the box, just these circles on the ends. And in fact, I'm just going to call that area. I'm not even, because I know it's going to cancel out anyway, and I'm not going to write out the formula for the area of a circle because I'm that lazy. Okay, so we end up with E times the area through which the flux is going, which is the area of that circle, and we have 2 of them, so we'll call it 2A. Now the enclosed charge here is the charge per unit area, which is sigma times the area over epsilon naught, and like I just said, these areas go away, and just like that we get our nice simple formula of sigma over 2 epsilon naught. Hooray for Gauss's law. Alright, see you next time.